Not null. Understanding the not null constraint. The not null constraint ensures a database column cannot contain null values, requiring a valid value during insert or update operations. It is a key mechanism for enforcing data integrity across major database systems, including MySQL, MariaDB, SQLite, Postgres, and SQL Server. When a column is defined as not null, a non-null value must be provided during data insertion. If no value is specified and no default value is set, the database will raise an error. Example. Consider the following table creation in Postgres. Create table users. ID integer. Username variable character, 50, not null. Email variable character, 100, not null. Here, username and email are marked not null, meaning they require values during insertion. Valid insertion. Insert into users, ID, username, email, values, 1, Alice at example.com. We specify a value for username Alice and a value for her email address. Invalid insertion. Insert into users, ID, username, values, 1, Bob. The email must have a value, it cannot be null. Best practices, use not null when a column must always have a value, like username or country. Data integrity is critical for the application. Avoid overusing not null, optional fields like phone number or email may allow null. Combine not null with default, discussed next, to provide a fallback value to prevent insertion errors. Default. The default constraint specifies a fallback value for a column when no value is provided during an insert operation. It is a key feature for ensuring data consistency and avoiding errors, especially when combined with not null. This constraint is supported across major database systems like MySQL, MariaDB, SQLite, Postgres, and SQL Server, though implementation details vary. Always consult your database's documentation for specifics, as features like current_timestamp may not be universally supported. If a column is not null and lacks a default value, an insert without a value for that column will trigger an error. Example. Consider the following table creation in Postgres. Create table users. ID integer. Username variable character, 50, not null, default guest. Created _at, timestamp default, current_timestamp. Insert example. Insert into users, ID, values, 1. Here we only insert a value for the ID. The username will be set to guest, and created _at will be set to the current timestamp. Practical tips for default values. When importing data, choosing distinct default values can simplify debugging and data validation. Here is a strategy I have found effective. Integers, use a value like all nines instead of 0. 0 is often a valid data point, but an extreme value like only 9 stands out in reports or exports. Text, set defaults to something like 20 letters Z, or Z. This is easily recognizable during data review. Dates can be tricky. I often import them as text with a default like 20 letters of Z or Z and convert them later to ensure accuracy. After a few imports, you will develop a sense of what default values work best for your workflow. Experimentation and adaptation are key. Unique. The unique constraint ensures that values in a column, or a combination of columns, are distinct, preventing duplicate entries. It is essential for maintaining data integrity in fields like email addresses, usernames, or other identifiers. Most database systems automatically create an index for unique constraints, to enforce uniqueness efficiently. Individual unique constraints ensures no two rows have the same non-null value in the specified column. There is also a composite unique constraint, we will get to that later. Null handling. MySQL, MariaDB, SQLite, and Postgres treat null as distinct, allowing multiple null values in a unique column. SQL Server permits only one null value in a unique column, unless a filtered index is used to allow multiple nulls. A filtered index, or partial index, is an index that includes only a subset of rows from a table based on a specific condition defined in a where clause. Not supported in all database systems. Example. Consider the following table creation in Postgres. Create table users 1. ID serial primary key. Username variable character, 50, not null unique. Email variable character, 100, unique. Insert example. Insert into users 1, username, email, values, Alice at example.com, this succeeds. Insert into users 1, username, email, values, Bob, null, succeeds, email null is allowed. Insert into users 1, username, email, values, Charlie, null, succeeds, multiple null emails allowed. Insert into users 1, username, email, values, Alice, new at example.com, fails, duplicate username Alice. The individual unique constraint on username ensures that each username appears at most once in the table. There can only be one row with username equals Alice. The individual unique constraint on email ensures that no two rows can have the same non-null email address. Alice at example.com can only appear once, but multiple null emails are allowed. Insert into users 1, username, email, values, Alice at example.com. Result, succeeds. Why, the username, Alice, and email, Alice at example.com, are new and do not conflict with any existing rows. Both satisfy their respective unique constraints. Insert into users 1, username, email, values, Bob, null. Result, succeeds. Why, the username, Bob, is unique and non-null, satisfying the not null and unique constraints. The email column allows null, and since no rows exist with email equals null, there is no conflict. Insert into users 1, username, email, values, Charlie, null. Result, succeeds. Why, the username, Charlie, is unique. A unique constraint in Postgres on email treats null as distinct from other null values, so multiple rows can have null in email without violating the constraint. Insert into users 1, username, email, values, Alice, new at example.com. Result, fails. Why, the username, Alice, already exists, from the first insert, violating the unique constraint on username. The email, new at example.com, is unique and would be fine, but the username conflict causes the failure. Now, let us take a look at the composite unique constraint. This allows duplicate username or email values, as long as the pair is unique. Create table users 2. ID serial primary key. Username variable character, 50, not null. Email variable character, 100. Constraint unique _name _email unique, username, email. The composite unique username, email constraint ensures that the pair of username and email is unique across all rows. Note that there are no individual unique constraints. As a result, we can have duplicate usernames, and we can have duplicate email addresses. What has to be unique is the combination username and email address. Insert into users 2, username, email, values, Alice at example.com, succeeds. Insert into users 2, username, email, values, Bob, null, succeeds. Insert into users 2, username, email, values, Alice, new at example.com, succeeds. Insert into users 2, username, email, values, Alice at example.com, fails. Insert into users 2, username, email, values, Dave, Alice at example.com, succeeds. Insert into users 2, username, email, values, null, test at example.com, fails, username column has a not null constraint. Apply unique to columns like email or username to prevent duplicates. Composite unique constraints are ideal for scenarios where a combination of values, like username and email, must be unique. Be mindful of database-specific null handling, especially when migrating to SQL Server. The automatic index created for unique constraints speeds up searches but may slightly increase write operation overhead. Attempting to insert a duplicate value triggers an error, so ensure your application handles these gracefully. Always verify your database's documentation, as unique constraint behavior, especially for nulls, can vary. You can see the outcome of the different statements in Postgres. Let us see why they succeed or fail. Insert into users 2, username, email, values, Alice, Alice at example.com. Result, succeeds. Why? The combination, Alice, Alice at example.com, is new and does not conflict with any existing rows, satisfying the composite unique constraint. Insert into users 2, username, email, values, Bob, null. Result, succeeds. Why? The combination, Bob, null, is unique. The email column allows null, and Postgres treats null as distinct from other null values in unique constraints, so no conflict occurs. Insert into users 2, username, email, values, Alice, new at example.com. Result, succeeds. Why? The combination, Alice, new at example.com, is unique. The composite unique constraint allows the same username, Alice, to be reused as long as the email differs from previous entries. Insert into users 2, username, email, values, Alice, Alice at example.com. Result, fails. Why? The combination, Alice, Alice at example.com, already exists, from the first insert, violating the composite unique constraint on, username, email. Insert into users 2, username, email, values, Dave, Alice at example.com. Result, succeeds. Why? The combination, Dave, Alice at example.com, is unique. The composite unique constraint allows the same email, Alice at example.com, to be reused as long as the username differs. Insert into users 2, username, email, values, null, test at example.com. Result, fails. Why? The username column has a not null constraint, so attempting to insert null for username violates this constraint, regardless of the email value or the composite unique constraint. Check. The check constraint. The check constraint enforces a condition on a column's values, ensuring that only data satisfying a specified Boolean expression is permitted. It is a powerful tool for maintaining data integrity by validating values, such as restricting ages to 18 or older or limiting statuses to predefined categories. A check constraint requires the condition to evaluate to true or unknown, null, for each row. If the condition evaluates to false, the database rejects the insert or update operation, triggering an error. Supported in most databases. Condition types. Numeric ranges, as age greater than 18. Valid categories, like status is active or inactive. Logical relationships, as discount is less than the price. Null values are treated as unknown, which satisfies the check condition. Named constraints, assigning a name, like constraint check underscore age underscore status, improves error messages and constraint management. Example. Consider the following table creation in Postgres, a single combined check constraint, or a table level check constraint. Create table users. ID serial primary key. Age integer. Status variable character, 20. Constraint check underscore age underscore status check, age greater than 18 and status equals active. But you can also use separate column level check constraints. Create table users. ID serial primary key. Age integer check, age greater than 18. Status variable character, 20, check, status equals active. These normally produce the same result. Let us insert some data and see the result. Insert into users, age, status, values, 25, active, succeeds. Insert into users, age, status, values, 16, active, fails, age less than 18. Insert into users, age, status, values, 20, pending, fails, invalid status. Insert into users, age, status, values, 20, null, succeeds. You can see the outcome of the different statements in Postgres. Let us see why they succeed or fail. Insert into users, age, status, values, 25, active. Result, succeeds. Reason, age equals 25 satisfies age greater than 18, and status equals active satisfies status equals active. Insert into users, age, status, values, 16, active. Result, fails. Reason, age equals 16 violates age greater than 18. Insert into users, age, status, values, 20, pending. Result, fails. Reason, status equals pending violates status equals active. Insert into users, age, status, values, 20, null. Result, succeeds. Reason, age equals 20 satisfies age greater than 18, and null for status is allowed, because check constraints in Postgres do not reject null values, unless a not null constraint is added. Considerations. Use check to enforce business rules, such as ensuring valid age ranges, predefined categories, or logical relationships between columns. Verify support in your database version, as older versions may ignore check constraints. Anticipate check violations in your application and provide user-friendly error messages. Naming constraints, as check underscore age underscore status, makes it easier to identify which constraint failed in error messages. Understanding auto-increment in SQL. Auto-incrementing columns are a common feature in relational databases. They are often used to automatically generate unique, sequential values for a column, typically a primary key. It ensures unique identifiers for rows and simplifies data management by automating ID generation. Most databases can have only one auto-increment column. Each database has its own syntax and behavior for implementing auto-increment. Please refer to the manual for the correct syntax. In Postgres, auto-incrementing values for primary keys can be implemented in several ways, offering flexibility for different use cases. The serial type automatically creates integer columns, small integer, integer, or big integer, that increment with each new row. Alternatively, Postgres supports the generated as identity syntax, with two variations: integer generated always as identity, which prevents manual value insertion, and integer generated by default as identity, which allows manual value specification while still auto-incrementing when no value is provided. Use big serial for large-scale apps. Let us take a look at what the syntax would look like for Postgres. Create table users, user underscore ID small serial, primary key. Create table users, user underscore ID integer, generated always as identity, primary key. Create table users, user underscore ID integer, generated by default as identity, primary key. When you insert data, the default setting would set the ID to 1, automatically assigned. To set a starting value for auto-increment in Postgres. Alter sequence user underscore ID underscore sec, restart with 1000. To change the increment value, for instance to 2. Alter sequence user underscore ID underscore sec increment by 2, restart with 1000. To view the last inserted auto increment value in Postgres, select curval, user underscore ID underscore sec, or use the insert statement, returning user underscore ID. Reuse of deleted ID in Postgres. Serial creates an integer column, backed by a sequence, independent of the table data, so deleting rows does not affect the next value. This means gaps are introduced in auto-incrementing IDs due to its sequence-based mechanism, which is used by both serial and generated as identity. If a transaction that inserts a row is rolled back, the sequence still increments because sequence values are allocated outside of transaction scope. This means the used ID is lost, leaving a gap. For generated by default as identity, you can manually specify an ID. If the specified ID is higher than the current sequence value, the sequence adjusts to continue from the highest value, potentially creating gaps. Returning the value of the ID column. Insert into users, user underscore ID, values, Alice, returning ID. View sequence details. Select asterisk from users underscore ID underscore sec. Dropping a table does not automatically drop its sequence unless cascade is used. To drop the sequence manually, drop sequence if exists user underscore ID underscore sec. Now, let us create a table and see all of this in action. Create a table with an auto-incrementing primary key. Create table users. User underscore ID integer generated by default, as identity, primary key. Username variable character, 50, not null. Serial is a Postgres-specific data type that auto-increments, starts at 1 and increases by 1 for each new row unless explicitly set. As you could see in the previous slide, there are 3 ways to create this table. Try it yourself with the other 2 versions. Time to insert users. Insert into users, username, values, Alice. Note, assigns user underscore ID equals 1, first sequence value. Insert into users, username, values, Bob. Note, assigns user underscore ID equals 2, next sequence value. Insert into users, user underscore ID, username, values, 10, Charlie. Note, explicitly sets user underscore ID equals 10, bypassing the sequence. Select set vol, user underscore ID underscore sec, 10. Note, sets the sequence's last underscore value to 10, after this, the next vol, user underscore ID underscore sec, will return 11. Insert into users, username, values, Eve. Note, uses the next sequence value, 11, so Eve gets user underscore ID equals 11. Select asterisk from users. User underscore ID username. 1 Alice. 2 Bob. 10 Charlie. 11 Eve. To prevent issues with sequence numbers in Postgres when using a serial or generated by default as identity column, you should manually set the sequence to the desired value after inserting a higher explicit value. For example, after inserting a row with user underscore ID equals 10, you should set the sequence to 10 to ensure the next auto-incremented value is 11. Set the sequence to 10 using, select set vol, user underscore ID underscore sec, 10. This ensures the sequence's last underscore value is 10, so the next call will return 11. While not always necessary, it adds a layer of security and predictability, giving you confidence in your data integrity. It is particularly valuable when auditors review your work, as it clearly documents your control over sequence behavior. This small extra step fosters trust and reliability in your database management. Let me show you how gaps are created. Insert into users, username, values, Peter. Delete from users where user_ID equals 12. Insert into users, username, values, Mike. Select asterisk from users where user_ID greater than 10. Output. User_ID username. 11 Eve. 13 Mike. You can see the output on the screen, user_ID 12 is missing. Also rolling back an insert creates a gap. Begin. Insert into users, username, values, Grace. Roll back. Insert into users, username, values, Heidi. Select asterisk from users where user_ID greater than 11. Output. User_ID username. 13 Mike. 15 Heidi. The user_ID 14 is skipped because the sequence incremented during the rollback transaction. You can view the last inserted value. Select curvel, user_ID_sec. To reset the sequence. Alter sequence user_ID_sec restart with 1000. Insert into users, username, values, Yvonne. Insert into users, username, values, David. Select asterisk from users. Output. User_ID username. 15 Heidi. 1000 Yvonne. 1001 David. Retrieve inserted ID using returning. Insert into users, username, values, Julia, returning user_ID. Output. User_ID. 1002. This inserts a row with username Julia and immediately returns the auto-incremented user_ID, like 1001, assuming the sequence continued from the previous examples reset to 1000. The returning clause is a convenient way to get the generated ID without a separate query. Primary keys in SQL. What is a primary key? A primary key is a column, or set of columns, that uniquely identifies each row in a table. It enforces not null and unique constraints. In most relational databases, primary keys also automatically create a unique index to optimize queries and maintain data integrity. Why are primary keys necessary? A primary key ensures each row is unique. This is critical for operations like updating or deleting a specific record. Primary keys enforce uniqueness, preventing duplicate records from being inserted. They also ensure that the key value is never null, guaranteeing that every row has a valid identifier. Primary keys are automatically indexed, which speed up lookups, joins, and searches. They enable reliable foreign key relationships in relational databases. Database operations, as replication, sharding, or clustering, rely on primary keys to track and synchronize records across systems. Now, how do we define a primary key? Let us start with the classic database design debate: meaningful or meaningless identifiers. Meaningless numbers, auto-increment, like 1, 2, 3. Pros. Auto-incrementing integers are straightforward to implement in most databases. The database handles the generation, ensuring uniqueness without additional logic. Integers are compact and efficient for indexing, joins, and lookups. Most database engines are optimized for integer-based primary keys. A meaningless key avoids embedding business rules that might change over time, making the system more flexible. The database ensures uniqueness, even in concurrent environments, without complex logic. Cons. A number like 948 does not convey any information about the customer or record. It is purely an internal identifier. If exposed in APIs or URLs, it can reveal sequential patterns or the total number of records, which might be undesirable for security or privacy. For human-facing systems, as customer support, a random number is not as intuitive as a formatted identifier. On the other hand, you can use meaningful, composite or formatted keys, like year plus month plus sequential number. Pros. A key like 2025040001 immediately conveys that this is the first customer from April 2025, which can be useful for reporting, customer support, or auditing. You could extend the format, like add a region code or product type, to encode more information if needed. Cons. Generating keys like 2025040001 requires custom logic to determine the current year and month and track the sequential counter for each month. Reset the counter at the start of a new month adds complexity compared to letting the database auto-increment. Resetting the sequential number every month introduces edge cases, like what happens if a record is created at the exact moment the month changes. How do you handle rollbacks or deleted records to avoid gaps or reusing numbers? If you do not reset the counter, you risk running out of numbers. A key like 2025040001 is larger than a simple integer. This increases storage and can slow down indexing and joins. Embedding the year and month in the key assumes your business logic will not change. If you later decide to group customers by quarter or region instead, you are stuck with a key format that is hard to modify without migrating all existing data. My opinion. I lean toward using meaningless auto-incrementing primary keys, simple integers. Keep in mind, primary keys are primarily for the database's internal use, uniquely identifying rows and optimizing queries. Primary keys are best kept simple and free of business logic to ensure performance and flexibility. If you need a human-readable identifier, consider adding a separate field, like customer_code, that is indexed but not the primary key. Let us add an auto-incrementing primary key to an existing table. First we create a small table and insert two users. Create table users. User_ID integer. Username variable character, 50, not null. Insert into users, user_ID, username, values, 1, Alice. Insert into users, user_ID, username, values, 2, Bob. We have our users table with two users in it, and user_ID 1 and 2. At the top of the screenshot you can see the inserts of Alice and Bob. Create sequence users_user_ID_sec. This statement creates the sequence. Alter table users alter column user_ID set default next vol, users_user_ID_sec. We use alter table to set the sequence as the default value for user_ID. Select set vol, users_user_ID_sec, select max, user_ID, from users. This sets the sequence's current value to 2, the maximum user_ID. The next call to next vol returns n+1 equals 3 in this case. Alter table users add primary key, user_ID. We add the primary key. Alter sequence users_user_ID_sec owned by users.user_ID. As a last step the sequence is tied to the column. Let us insert another user, Eve. Insert into users, username, values, Eve. Select asterisk from users. User_ID username. 1 Alice. 2 Bob. 3 Eve. Foreign key. A foreign key is a column, or set of columns, in one table that references the primary key in another table. It enforces referential integrity, ensuring that the foreign key value matches an existing value in the referenced table's primary key. The primary key in the parent table is referenced by the foreign key in the child table. This creates a parent-child relationship, ensuring data consistency, as no order can reference a non-existent user. We created the users table earlier, so we can use that table. Now we create our child table, orders. The users table has a primary key, user_ID, and the orders table has a foreign key, user, referencing users, user_ID. Create the child table orders. Create table orders. Order underscore ID, serial primary key. User, integer not null. Order underscore date, date not null, default current underscore date. Foreign key, user, references users, user underscore ID. Explanation of the orders table. Order underscore ID, the primary key for the orders table, also auto-incrementing. User, the foreign key that references the user underscore ID column in the users table. It is set to not null to ensure every order is tied to a valid user. Foreign key, user, references users, user underscore ID. This defines the foreign key constraint, linking user to users.user underscore ID. Let us insert an order by Alice. Insert into orders, user, order underscore date, values, 1, 2025-0531. And an order by an unknown user underscore ID 999. Insert into orders, user, order underscore date, values, 999, 2025-0531. This result in. This insert violates the foreign key constraint orders underscore user underscore ID underscore foreign key. Detail, key, user underscore ID, equals 999, is not present in table users. Every table should have a primary key to uniquely identify each row, such as user underscore ID in the users table or order underscore ID in the orders table. In Postgres, you can use the serial data type for auto-incrementing IDs. Use foreign keys to enforce relationships between tables. For example, a foreign key like user in the orders table references users, user underscore ID, to ensure referential integrity. Ensure the foreign key and the referenced primary key have identical data types, such as integer for both users.user underscore ID and orders.user. Foreign keys support several options for handling updates and deletions. On delete cascade, automatically deletes child rows when the parent row is deleted. For instance, deleting a user removes all their orders. Example, constraint. References users, user underscore ID, on delete cascade. On delete set null, sets the foreign key to null when the parent row is deleted, if the column allows null values. Example, constraint. References users, user underscore ID, on delete set null. On delete no action, prevents deletion of a parent row if child rows exist, such as blocking user deletion if they have associated orders. Example, constraint. References users, user underscore ID, on delete no action. The onUpdate clause offers similar options, cascade, set null, set default, if a default value is defined, or no action. Indexes. An index is a database structure that improves the speed of data retrieval operations, such as select queries, by allowing the database to locate rows more efficiently. Think of an index like a book's table of contents. Instead of scanning every page, you can quickly find the relevant information. Indexes store a subset of a table's data, typically one or more columns, in a format optimized for fast lookups. When a query searches for data, the database uses the index to narrow down the rows to examine, reducing the need to scan the entire table. Benefits of indexes. Indexes significantly speed up select queries, especially for large tables or frequent lookups. They optimize where, join, order by, and group by operations. Trade-offs of indexes. Indexes consume additional disk space, as they store a copy of the indexed data. Insert, update, and delete operations are slower because the index must be updated alongside the table. Indexes require periodic optimization or rebuilding to maintain performance, especially in heavily modified tables. Always consult your database's manual for the correct syntax and the appropriate index type for your needs. Practical considerations. Create indexes on columns frequently used in where clauses, join conditions, or sorting operations. Avoid over-indexing, as too many indexes can slow down write operations and increase storage needs. Analyze your application's query patterns to decide which columns need indexes. While all RDBMSs support indexes, their implementation varies. Check your database's documentation for specifics. Indexes are a critical tool for optimizing database performance, but they require careful planning to balance query speed with write efficiency and storage costs. Let us take a look at databases and their index types. MySQL, B-tree, hash, full text, spatial, multi-valued. MariaDB, B-tree, hash, full text, spatial, virtual column indexes, are tree often included in spatial. SQLite, B-tree, FTS3/FTS4, FTS5, are tree. Postgres, B-tree, hash, gist, spgist, gin, brin, bloom, partial. SQL Server, clustered B-tree, non-clustered B-tree, full text, spatial, column store, filtered, XML, memory optimized hash, memory optimized range. B-tree indexes, balanced tree indexes, are the default and most widely used index type in relational databases. They are versatile, support a variety of query types, and are critical for enforcing uniqueness, as in primary keys or unique constraints, and optimizing performance. B-tree is a balanced, hierarchical tree structure, and enforces uniqueness for primary keys or unique constraints, like no duplicate email values. Speed up queries involving equality, lookups, range queries, as greater than, less than, between, sorting, order by, and joins. Index columns are frequently used in where, join, group by, or order by clauses. General purpose indexing for structured data, like integers, strings, dates. It is the default index type in most databases, making it portable. Not efficient for full text search, like searching for words in a large text column. B-tree indexes require additional disk space, especially for large tables. Updates, inserts, and deletes can be slower due to index maintenance. Less effective for columns with few unique values. Postgres uses B-tree as the default index. Create index IDX_email on users using B-tree, email. It supports partial indexes, create index, where condition, and expression indexes, index, upper, email. Full text indexes. These indexes are designed for searching large text data, such as articles, descriptions, or documents. They optimize queries that match words or phrases within text columns. The index stores a list of words and references to rows containing those words, enabling fast keyword searches. It ignores stop words, like the, and, or a, and applies stemming, snowball stemmer, which reduces running to run. For instance, they are used for searching product descriptions, like finding products with wireless headphones, or searching features in blogs, forums, or content management systems. Full text indexes only support text search operations, not equality, range, or sorting. They can be large for text-heavy columns, especially with frequent updates. They support language-specific stemming, ranking, and custom dictionaries for multilingual searches. They require specific syntax or configuration. Postgres uses GIN indexes with TS-vector and TS-query for full text search. Supports language-specific stemming, ranking, and complex queries. Highly customizable, such as custom dictionaries and multilingual support. Let us create a table and an index. Create table documents. ID serial primary key. Content text. Create index, IDX_FTS on documents, using GIN, _TS vector, English, content. The GIN index optimizes searches by pre-computing the content column, making queries much faster. To find a search term in the content field, use. Select asterisk from documents, where to underscore ts vector, English, content, at to underscore ts query, keyword. Explanation of the select statement. Select asterisk from documents, retrieves the column's ID and content from the documents table. Where to underscore ts vector, English, content. The content column is converted into a ts vector, a data type that represents the text as a sorted list of unique words. English specifies the English language. Stemming is applied. If the content column contains the cat is running, it produces a ts vector like cat, run. To underscore ts query, keyword. Converts the search term keyword into a search expression with, run for running. At operator. The at operator checks if the ts vector, the content column, matches the ts query, the search keyword. If the content contains the keyword, it returns true, and the row is included in the results. For example, to underscore ts vector, the cat is running, at to underscore ts query, run, returns true, running stems to run. How it works. The query scans the documents table, converting each row's content to a ts vector and checking if it matches the ts query for keyword. Rows where the content contains keyword, or run for running, are returned. Trigger. Triggers are database actions, as insert, update, delete, that automatically execute custom logic. They can mimic some constraint-like behavior, like enforcing complex rules beyond check. Triggers are not constraints, but can complement them. Triggers are supported by all databases, but syntax and capabilities vary. I am using Postgres for this, since it requires some extra work, as creating a function. The other databases, like MySQL, MariaDB, SQLite, and SQL Server do not need a function. But first, let us create a simple table. Create table users. ID serial primary key. Name variable character, 100. Last underscore updated timestamp. In Postgres, triggers call a function written in PLPG SQL, or another language. This function will set the last underscore updated column to the current timestamp when a row is updated. Create or replace function update underscore last underscore updated. Returns trigger as $. Begin. New dot last underscore updated equals current underscore timestamp. Return new. End. $language PLPG SQL. What happens here? Create or replace function defines a function named update underscore last underscore updated. Returns trigger indicates this is a trigger function. New dot last underscore updated equals current underscore timestamp updates the last underscore updated field of the modified row. New represents the new row data. Return new returns the modified row to complete the operation. Language PLPG SQL specifies the function uses PL/PG SQL. Now, we have to create the trigger. Create trigger underscore update underscore timestamp. Before update on users. For each row. Execute function update underscore last underscore updated. What happens here? Create trigger defines a trigger named trigger underscore update underscore timestamp. Before update, runs the trigger before an update operation. On users, applies to the users table. For each row, executes the function for each updated row. Execute function update underscore last underscore updated, calls the function we created. We insert a record into our table, the field last underscore updated gets its value, the current timestamp. Insert into users, name, last underscore updated. Values, Alice, current underscore timestamp. Let us see what the content is of our users table. The next two slides show the output of all our statements, including their results. Select asterisk from users. Now we do an update, the field current last underscore updated should get a new value. Update users, set name equals Alice Smith where ID equals 1. When you update a row in the users table, like change the name, the trigger underscore update underscore timestamp trigger fires before the update is committed. It calls the update underscore last underscore updated function, which sets the last underscore updated column to the current timestamp. The updated row is then saved with the new timestamp. Again, we check the content of our table to see what has changed. Select asterisk from users. Exploring triggers in Postgres. This slide demonstrates creating a table, function, and trigger to manage a last underscore updated timestamp. The next slide shows the trigger in action with an update statement. Pause the video to dive into the code details. We discuss the importance of the last underscore updated field on the next slide. Why track timestamps in your tables? Without timestamps, you cannot pinpoint when data was added or changed. Imagine auditors asking, which users were added in December, or what changed last month. Without tracking, you are stuck. Add these fields to every table. Date underscore created, to set the date a row is inserted. Last underscore updated, tracks the latest change. Use triggers to automate these updates, keeping your application logic clean. Yes, it takes a little setup, but it is a small price to pay for audit-ready data. You will thank yourself for later. That's a wrap for this lesson. You have mastered constraints. Great work. In our next video, we will dive again into select and more. Keep practicing to solidify your skills, and I see you in the next lesson.